what I want to do today is kind of stick handle through UPS applications, how to pick the right UPS, some of the criteria along the ways, maybe share with you some of the insights I have from things that have propped up or common questions I'm asked that you might be facing or may face in the future and need a solution to. I then want to talk about the weak points of the UPS system, in particular the battery, right? And what we can do to maximize that. And then finally, as I indicated, bring it back into a software monitoring. How do we bring all this back together? For something as critical as power is, surprisingly, it's not clean. And surprisingly, it doesn't have to be clean. There's no law or justification or legislation of any sort that says this critical lifeline is an absolute must. We can't hold anyone accountable. Power can go on or off at any point in time, and there's not a thing we can do about it. It's pretty scary. And our studies have shown, and our typical experience has shown, it isn't the most reliable. In fact, most studies, depending upon jurisdictions and climates, and there's a lot of factors out there, but we're typically about 99.9%, which isn't a bad thing. I know from my own personal experience, we had a power failure last Friday at home, a 3-hour power outage, and it was the first time in a long time. Generally speaking, it's pretty reliable. But if I'm talking about a 24/7 operation, if I'm talking about a piece of equipment, an IT, a semi-processor, a semiconductor, intelligent storage device, communications device, pretty much anything that uses a semiconductor, that's critical, right? I mean, that 99.9 is just not enough. There's a downtime associated, a failure associated with that, and that's really what we need to protect. And the most important thing is even short power outages. Doesn't matter the time. Doesn't even matter if it's an outage. We keep saying outage, but a short power anomaly can cause us untold amounts of pain. A couple of things here is that the power problems and the anomalies aren't getting any better. In fact, it's going to get worse. I used to do a presentation. I used to say, you know what? There's two things that make up a power problem. One is you have to have the anomaly. But the second part of that, which turns the anomaly into a problem, is you got to feel some pain. Right? If you don't feel the pain, then who cares if you had the outage? Who cares if you have transient activity? It doesn't matter. There's no power problem. It's a power event, but you've implemented a solution to avoid the problem. Well, there's another piece to the puzzle, and that's what is the load? Right? When we look at 10 years ago, 50 years ago, 15 years ago, when we were talking about communications through an RS-232 cable or peer-to-peer communications, right? We didn't know what a network was back then. Well, a 1 millisecond power interruption resulted in the loss of 20 bits, 10 bits of information. Big deal, right? It's kind of like reading a book and missing a couple pages. I mean, when I read, I miss every 10th word, and I still get the gist of the story, right? So no problems. We didn't have power problems, right? Because the loads weren't impacted by it. Our communications networks weren't driven to maximum performance, right? Our IT equipment was only operating at 10%. Today, virtualization, cloud computing, all of the technologies, we're trying to drive things to 100%, right? You talk to the data cabling world, and they're talking about 100 gig communications. Right? When is it going to stop? So now you deploy a 10 gig network, and please don't quote me on these numbers, but you deploy a 10 gig network. Now in that same 1 millisecond interruption or iteration, I've now sent 50,000, or I think it's 500,000 bits in that same iteration. Now I can feel some hurt, right? Now I'm reading that book, but I've just missed, 50 pages. I've lost a whole bunch of information. Now, it may accommodate or may not, but my susceptibility to that risk is just massive. So as I deploy this new technology, I am now becoming more susceptible to these power problems. So again, power is not clean, not guaranteed reliability, and my pain and my tolerance to it has gone down, so I'm going to increase my risks. So power is an important, critical piece to the overall puzzle. Shown here is the offering below 20 kVA, typically our single phase offering. And there's a lot of different models, a lot of different SKUs. In fact, there's over 400 different models to choose from. And I often get asked the question, well, why would you need so many? Likewise, when you get above 20 kVA, we start getting into a lot more of these models. Now, these are three-phase UPSs, so there's your first distinction between the two, right? Previous page was single-phase, this page is three-phase. But still, there's a lot of different offerings. Why do you need so many? Well, because every application is slightly different, right? If you recall, from a power quality perspective, it is the 10,000 square foot data center, right? 3 megawatts of power requirement. It is each of your home offices, each of your personal computers under your desk. It's every rack. It's grocery stores. It's retail environments. It's industrial mining environments. It's anywhere we need and rely upon a computer. Pretty much everywhere. So all these models really simply cater to those. And these are the top 10 questions, if you will, to ask, or application pieces, which really help you navigate through that minefield and say, this is the model I need. And online you find configurators that ask these questions, provide the pull-down menus with the options that help you zero in on the particular model. One of the questions I often get asked is, hey, can you send me a general spec? I can't, unfortunately, because every application requires a little bit of different. It's not a cookie-cutter approach. As I indicated yesterday, there's not one solution that fits all bills, but there is fundamental operating and selection principles that can be applied, and here's the first 10 of them that really help us zero in on what the right one is. So these 10 questions and the answers subsequently to them help you pick to the right spec, the right requirement. And the first is the power environment. In fact, I've got a problem with the order of these. I would say number 3 is the first. What is it that I'm trying to protect? How big is this? What is my kilowatt requirement? Is it a home office desktop PC, right, with a 500-watt power requirement? Is it a gaming PC? Because I can't afford to lose that game that I'm playing. But then I'm into a 2-kilowatt power supply for a gaming machine because of the processing speeds to it, or video graphics or editing or anything like that. Or am I talking about a rack? Maybe I'm talking about a comms rack with a brand new Cisco switch operating at 7 kilowatts. Maybe it's got some server equipment in there, so now I'm talking about a rack with 12 kilowatts. Maybe I'm talking about a row of 10 racks. Maybe it's a floor with 100 racks. So that determines what my power requirement is. Once I have my power requirement, by simply calculating all the loads and adding them, once I have my power requirement, it then tells me whether I'm into a single or three-phase. Typically, single-phase applications go up to about 18 kilowatts. Beyond 18 kilowatts, I need to get into a three-phase type of application. So that immediately kind of narrows it down. My installation environment, and I've got some upcoming slides on this, but is it a rack-mounted application? Is it a tower application? That'll decide it. Next, I get into my availability, scalability, additional feature sets that might help me stick handle through that minefield. Power distribution. Touched on this a little bit in previous presentations, but really, what is the plugs you need? If I'm backing up 20 devices, kind of need to know what their plugs are so that I can do that connection. And then we talk about the proactive measures, the services, the total cost of ownership, the budgeting, the number side of it, as well as how do we tie it all together from a communications perspective. So form factor, function. Right? I've got desktop UPSs and typical CPU type of environments, maybe in a panel board, right? I've got a wall-mounted panel of 12 inches deep. I need a UPS that'll sit in the bottom of the panel, right? Doesn't need to be rack-mounted, don't need that form function. I just need nice, small, compact brick. It's referred to often. Maybe I'm putting the UPS at the demarcation point at the entry to a building. You know, the plywood backing, right? That I never needed to worry about before? Well, today, there's active components. There's a switch in there. There's a comms. There's maybe a modem, a cable modem built in there, right? I now have to provide that as a power quality device. Wasn't there before, but as technology advances, the need for power quality comes into play. So I have wall-mounted UPS solutions. By far, we're seeing the largest increase in rack-mounted. That demarcation point, that plywood backing point, is now being replaced with a cabinet that simply sits on the wall, I'm sure you've all seen it. Next time you're in a Home Depot, look up. Behind the cash, there's really a 42U rack typically sitting on the wall. That's where the demarcation point has kind of moved towards. To accommodate these changes and to make sure that an investment today can be expanded and modified into the future, you have what's referred to often as a 2-in-1. A UPS that can be used as a tower, a tall, thin tower, and then when it's migrated into a rack, you simply turn it on its side and rack mount it. So again, allows for that future use of capital. Yesterday, we spent the whole hour talking about scalability and scalable UPS systems, right? But here we're talking about pay as you grow. If my load today is a 3 kilowatt requirement, I can put in a 3 kilowatt power module into an expandable chassis. As my loads expand, as I need another 3 kilowatts, I can add another 3 kilowatt power module and create a 6 kilowatt UPS, or a 9 kilowatt, or a 12 kilowatt. Here's a typical picture of what would look like a 3 to 18 kVA expandable UPS. Similarly, in our floor here, we've got a 12 to 60 kilowatt expandable UPS. So again, scalable type of UPS systems. Large tower UPS, right? And really, the only thing that differentiates the sizes is the current requirement. Right? The larger size, you need more and more current. The components get bigger and bigger and bigger. Here we're looking at an 80 kVA, which is a 19-inch fridge. Right? When you get into the larger UPSs, now they become just bigger fridges. And literally, they're fridges. Each section could weigh up to 4,800 pounds, 5,000 pounds. When you get into a battery cabinet, you got to handle them differently. They're no different. A battery pack is a battery pack is a battery pack. This big battery pack, this little one, or the ones internal to here, it's still a battery pack. It's because of the size, it's bigger. And it brings a whole bunch of different challenges. It's not something you can just pick up and move around. Brings us to the plug conversation, right? When we think about a regular wall plug, a 5-15 it's called, right? 5 being 120 volt, 15 being the current rating, 15 amp. And I multiply the two together. So 120 times 15, I get a total of 1550 VA. Sorry, 1440 VA. Or 1500 VA, which is the maximum I can put onto one plug. So keep that in mind. If someone's saying they have, the load requirement is 2 kVA, but I need a 5-15, well, you can't put 2 kVA on that plug, right? As your loads increase, you have to move to a 20 amp plug or a 30 amp plug. A 5-30, 120 volt 30 amp, is a 3 kVA type of application. Once I go beyond that requirement, I have to go into a 208 volt or a two-phase type of solution, similar to our fridges and stoves in our houses, or fridges anyway. Stoves anyways, right? Which are typically about 7.2 kilowatts. If I turn on the oven and turn on all the burners, it's about 7 kilowatts for a stove. So that's a 6-30 or a 14-30 if I have the neutral. So the plug requirement is really tied to the size of the UPS. And that's why you have the different varieties there. When I get beyond, I have to worry about my loads, right? Even in a 1 kVA or a home application, right? In the simplest of cases, right? I'll have a modem, I'll have a router, I may have a printer, I may have 5, 6 devices. Hopefully they all have the same plugs. But as I get into a rack, and as I get into the larger UPS systems, I really have to know what plugs are on what devices. Also, when I get into the IT and the telephony as well as the datacom world, take a Cisco for example. You open up a Cisco catalog page and you turn to page 4 of the order sheet, and I've got a choice of 8 different line cords I can purchase. Well, which one of them are you going to purchase? Because the UPS solution needs to provide a subsequent receptacle for that line cord to plug in. We spend a great deal of our time, once the UPS arrives on site, saying, oh, well, okay, let's swap out that line cord. Let's make that marrying, and we do after delivery engineering to try to make the mate fit. Very critical from a UPS application. And this, again, drives those different models. Small single-phase UPSs, you're going to have receptacles on the back. So if you need different receptacles, we have to switch to a different model or a different type. Larger systems, typically 10 kilowatts to 20 kilowatts, you're going to have a doghouse or a distribution panel on the back of the UPS. And in that distribution panel, we insert the receptacles required. You're going to have, very similar to the equipment, you're going to have a checklist saying how many of these do you want, and you buy them a la carte, if you will, and you embed them in there. We get into larger three-phase. Here we're talking about terminal blocks, right? Once I go beyond 30 amps or 50 amps, I have to go to a terminal block input. Question is, how do I convert the terminal block to receptacles? And I do that through distribution panels. When I'm running a circuit into a rack, let's say in a given 42U rack, 19-inch enclosure, I have 20 devices that I need to power up. Does it make sense to run 20 circuits into that cabinet? No. Right? I'll run one three-phase 30-amp circuit into the cabinet, and then I'll use a vertical power strip or an enclosure PDU or an ePDU to distribute the power. So I have 30-amp three-phase coming in. I've got 3 circuits, phase A, phase B, phase C, with the appropriate plugs I need. So I use the distribution, and that helps me whittle through that minefield of options that I have available. And I'll come back to this in a moment, but while I have this slide up here, as I'm introducing all of these touch points, these interfaces, I also introduce the ability to do power monitoring. Most of these vertical power bars have power meters, so I can give you current per phase. Most of these power bars have power meters on the individual receptacles. So I can tell you J14 is drawing 8 amps. I can turn those receptacles on and off, right? I'm building a large system. I've designed it for 18 kVA. Last thing I want is somebody to arrive on a floor and start saying, oh, hey, look, I want to plug in my drill, or I want to plug in a vacuum cleaner into that, right? It happens. It sounds stupid, but it's the number, it is so critical. And when I hear people talk about downtime and what happened, well, you wouldn't believe it. Is probably typically how the story starts. It happens. These give us the ability now to control and turn off receptacles as we need to. Brief background here into the why we're here. And it's really about power problems and power anomalies. I generally spoke about the power anomalies. I'd like to just break those down into a little bit more detail so we understand. And this is really a preamble into the different technologies that exist out there. We took a look at IEEE, and we're trying to figure out how do we best speak to the challenge at hand. And we looked at IEEE, and we found that, you know what, there's really 9 different types of power problems in the marketplace and that we're susceptible to. And me being the simpleton that I am, I like taking this and even breaking it down even further into 3 categories. If you look at the first 3 power anomalies, being power failure or long-term power outage, a sag or a short-term power outage, and an impulse or a power surge, lightning, those 3 items, if they were to occur right now, we would be immediately aware of their occurrence, right? If power failed, we would be sitting here in dark, may have an emergency light or 2, but we would know immediately. If lightning struck, we could either feel it, depending upon how close we were, or we could smell it, depending upon the equipment, but you would kind of know that it occurred. So these incidents are pretty obvious. And when we think about power anomalies, when we think about protection, we immediately gravitate to these 3. And if we've addressed the 3, we're in good shape. Well, yes and no. Because there's 2 other power problems called overvoltage, undervoltage. They're not steady state. They might be picked up, might not be picked up. When the air conditioner on the roof here turns on, we may see the lights dim a little bit. When it turns off, we may see an increase in the power, right? We see it in our homes with dishwashers and heavy loads when they turn on, right? We may or may not see these fluctuational problems. Guaranteed our computer equipment is, and the IT equipment is seeing it, right? This sudden overvoltage, undervoltage, which causes strain upon the circuits. Then we get into the last 4. Line noise, frequency variations, transients, harmonic distortion, steady state type of problems that exist in an electrical network or an electrical infrastructure, typically induced by the loads themselves in the environment itself. This isn't a utility problem typically. This is in the buildings that we have. And they're steady state. They're just a function of the nature of the application or the environment we operate. It's not an event. It's not something. It's part of an electrical problem. It's also invisible, right? I can't tell you if there's an electrical line noise. I can't tell you what the harmonic distortion is in this building at that receptacle. Now, I can take a meter, and I can go there, and I can meter it, and I can tell you, okay, at this instant, it's pretty good. Pull it out, I can't tell you what it is anymore because it could happen or not happen. But the loads are susceptible to this information. The loads will see it. Now, let me state a lot of improvements have been made to the power supplies, right? Universal power supplies, they can operate in different voltages. They're more susceptible to interruptions. They can tolerate 10 millisecond outages, right? We look at the Sabima curve and all that kind of information. So power supplies have improved their tolerances out there. However, their specifications are produced in a test lab environment where there is no power anomalies. They take voltage tolerance independently from line noise tolerance, independently from outage tolerance. So they're not really real-world experiences. They're based on clean, filtered, regulated, perfect power. It's very similar to an athlete, right? You know what? All of us can operate fine at high altitudes and low altitudes within reason, right? Sure, if we go mountain climbing, we'd be impacted. But generally speaking, we can function and talk at various different altitudes. An athlete, however, who's running at full performance, struggles when they go to Denver, right? Struggles, and various different numbers have put it out there, 5 to 10% reduction in performance when they go to Denver. Why? Because of altitude. So as we drive performance, as we drive equipment to optimal performance, we become a little bit more susceptible to power problems. So what's my power solution? How do I solve these? And I purposely avoided tap switching transformers, surge suppressors, line conditioners, line regulators, all of the other power products that really address individual kind of components, right? There's HRT, harmonic mitigating transformer solutions, if harmonic distortion. And they're all really designed for one or two devices. Focusing on UPS, there's 3 technologies of UPS. And they address different varying pieces of the power anomalies. The first, being an offline or level 3, addresses well, we could also say they all address the obvious ones, right? And that has typically been, hey, as long as you address these 3, you can be called a UPS. The reality of it is, though, we do have other power problems we need to consider. A line interactive or a level 5 addresses over and under voltages, but then stops. A true online will address all of them. So if you want to guarantee clean, filtered, regulated power, you almost have to go with an online double conversion technology. Well, let's see why. If I look at an offline UPS, basically my power components, the battery and the inverter, are sitting offline waiting to be switched into service. My loads are fed directly off of the utility. Sure, I have a surge suppressor, right? It's more designed to protect the UPS than the given loads, but it's there, and it's really, the clamping voltage is designed around high voltage spikes, not low transients. But this is the typical power path of this UPS. Now, if I have a power outage or I have one of the incidents, it's going to switch to the UPS, and now I've got a battery feeding an inverter taking that DC, re-inverting it back to AC, giving me power to the load. And typically there's a 2 to 6 millisecond transfer time. But now I've got clean, filtered, regulated power for 5, 10, 15 minutes, depending upon the battery bank. Now, battery's like a loaf of bread. How long it lasts depends on 2 things. How many times I cut into it, and how thick each slice is. With an offline UPS, it is my only means of power quality device. So I'm going to use it every chance I get, and I'm going to take a lot more slices out of it. Typically, an offline level 3 UPS, we're seeing approximately 2 to 3 years life expectancy on the battery, because I'm cutting into it and I'm taking those slices. Also with an offline, For the fluctuational, if they're not as severe and can't be considered as a power outage or a surge, as well as the harmonics, frequency variation, switching transients, and distortion, they're allowed to pass unabated through to the load. So I've got a UPS on there, but I'm still getting berated with these devices. Why? Because it's just simply, it's monitoring the voltage before it switches. Another problem with this is the components are offline. If they've failed, if the battery's failed, how do I know and when do I know they've failed? When I have a power failure. When do I need those components to operate? When I have a power failure. So eventually, at some point in time, I'm going to have a component fail and I won't know it's failed until I go to use it. And guess what? I'm going to have a failure. So it's really a reactive kind of approach to power quality. Now, it's very cost effective. If my risk isn't that large, I may want to go this route. If my load isn't that critical, I may want to go this route. It's a reactive approach, but it's very cost effective. But my problem is in the total cost of ownership in that the battery is consumed in about 2 to 3 years. So what I want to do is I want to extend the life of batteries. And how can I do that? Well, first and foremost, use it less. If I don't need to use the battery as often, if I don't take as many slices out of it, I'm going to increase the lifespan of the battery. So what I've introduced here, very similar to the level 3, or the offline. However, I also have a buck boost circuit in here, and I'll talk about that in a moment. So in normal conditions, the UPS is offline, power is flowing through normal mode directly to the load. If I have one of the incidental type of power problems, a power failure or an extreme sag, it's going to transfer it to the battery circuit and supply power to the load. However, where it differs from the level 3 is that it has a scenario and a situation of a buck boost, basically an electronic tap switching transformer with DC or capacitance built into it to ride through the switching, where we're going from buck mode and boost mode. So if I have a 10% overvoltage, I'll buck it down to nominal voltage. If I have a 10% undervoltage, it'll boost it up to nominal voltage. What I'm doing through the buck and boost is I'm saving slices on the battery. If I can save slices on the battery, I increase the lifespan of the battery, or of the battery, and therefore of the operation of the UPS. So now I'm increasing my lifespan to typically about 4 years, 3 to 4 years, anywhere from a 25 to a 50% increase in battery time. However, the last group of power problems, it's not really designed to protect against those, right? It's designed to really pass those through to the loads. Now, the argument here is that the loads have become a lot more robust and can tolerate these anomalies, and that may be the case. I had one client and friend and associate of mine who switched jobs and came to the new jobs and was wondering, hold it, how come my fans are failing 2 years before they were on the previous job I had? And he realized that this new role, this new application is using level 5. So a lot of these devices are causing a longer term impact and degrading the life and the performance. So how do I guarantee clean, filtered, regulated power under all circumstances? Right? And it really comes down to creating the power under all circumstances to be clean, filtered, and regulated. I don't care what the power problem is. It's very similar to distilled water. Thank you. It's very similar to distilled water. How can I guarantee pure, clean, filtered water? Well, you distill it. Go through the process. Take impure water, convert it to steam, and then condense it to pure water. How do I get clean, filtered, regulated, guaranteed clean power? I take AC power from the utility, full of impurities or possible power anomalies, and I take it through a double conversion process. I rectify it to DC, and then I re-invert it back to AC under all conditions. The inverter is always supplying power to the loads. In fact, many loads out there in the real world have never seen utility power on them. They've always been fed from an inverter grade power. And I'll give the engineers at Eaton a lot of credit. Because they were developing the power, they chose to develop and create inverter outputs without power anomalies on them. So the inverter output is a guaranteed perfect sinusoidal wave, perfect 60 hertz, perfect amplitude of 120 volts. Yes? By the rectifier. You're talking about the voltage, right? The inverter will basically, the inverter regulates the output sine wave depending upon the loads, right? The loads will pull harmonic currents from the inverter, from the power source. Those harmonic currents will impact the voltage waveform created by the power supply. The output waveform will be adjusted voltage-wise to accommodate and support those harmonic loads coming in to reduce the voltage THD to less than 5%. Now that is adjustable on some models, but really less than 5% voltage THD is typically in better than anywhere up here. That's on the load side. So the inverter is also regulating the output voltage THD on a regular basis. Now, former designs where we're using SCR-based rectifiers on the front end, you ran into instances where this rectifier was creating 34% harmonic currents onto the grid and upstream. Well, two things. At the time, this harmonic current requirement onto the grid was no worse than the harmonic current in the loads. Even though it was high, the technology at the time was still better than your typical loads, than your switch mode power supplies at the load. So it was an improvement. Wasn't ideal. Fast forward to today's technology, what you will have is you have IGBTs now in the power conversion components of the rectifiers. So you have an IGBT front end which will self-regulate and limit the input current THD to less than 4%, typically about 3.5% on the front end. So again, today's technology, it limits the input current draw from the utility to less than 4%, typically 3.5%, and it will self-regulate the output voltage to less than 5%. Now, as good as it is in cleaning up all the power problems, so regardless of what comes in, the double conversion process cleans it up. There comes a point where you simply cannot clean up and create power, right? The power voltage is just not there. The amplitude of it's not there. It could even be a power failure. So even the online needs to switch to battery to provide that power. Two things, it's not switching the load. The load is always fed off of an inverter. It's an internal switching. So there's no impact, no transfer time to the load. But more importantly, this is only used when it can absolutely no longer clean up the power. So we have scenarios where we have 84 volts, 85 volts coming out of the utility or out of the wall plug, and the UPS is creating 120 without using the battery. It'll run forever in that device. So again, by not using the slices out of the battery, we extend the life of the battery. Typically on an online double conversion, you're going to get 5 years plus out of the battery. And the other nice or critical design feature of an online UPS is the fact that because you're always using the components, if there is a failure, you immediately know of the failure. The UPS will transfer to bypass and isolate the power components and notify you of the failure. And here's where it gives you as an operator or the business unit the choice, the opportunity to make the decision. Yes, my load is fully exposed to all power anomalies on the utility. I can choose to either turn off the loads or I can choose to run them in this manner. The choice is mine. An analogy here or a sideline is if you take Ontario lotteries at 5 minutes to 9, they may choose to run in bypass mode. There's a lot of revenue being generated, and a lot of people are buying tickets. There's a reason to keep the network operational and assume the risk. If it happens at 9:15, after the draw or after tickets have closed, there's no revenue being generated. It does not make a business sense to operate or accept the risk in that environment. So the UPS pretty much puts the decision back upon the business unit to make the call on how to operate. So even if there's a failure, there's no problem because it gives you the opportunity to react and resolve the problem. Does that kind of make sense? The next piece I want to kind of table and discuss is, quite frankly, the Achilles heel of UPSs. Far too often I get the call in saying, hey, the UPS failed. Well, with all due respect, it wasn't the UPS, it was the battery that failed. The battery is a consumable device. It is the lifeline. Typically, that's the number one by far scenario under which the UPS fails to perform its functionality is because the battery has been consumed. So let's take a look at the battery. What is the battery, right? Battery is basically an electrical chemical process of plates with an electrolyte between plates. You charge up the battery to store this energy within the plates, and then it will discharge down the batteries. Now, UPS batteries are very different in that they're designed to deliver a large amount of power for a relatively short period of time, 10, 15 minutes. So the plates are relatively thick to allow for that large power hit on them. But they're not really undifferent than any other technology out there. When we look at the design life of a battery, and typical applications will have two. Single-phase UPSs, the small, they look like motorcycle batteries, for lack of a better analogy. They're typically a 5-year or 200 complete discharges. 200 complete discharges uses up the battery in the whole charging process. 5 years because there's a lifespan to the electrolyte within a battery. Larger 3-phase UPSs typically use a 10-year design life. Still the 200 complete discharges, but the electrolyte will last a little bit longer. Now, even though it's a 10-year design life, the typical experience has been 4 to 6 years out of that 10-year battery. Whole different discussion as to how that works, but again, typically 4 to 6 years. So what contributes to a battery failure? We talked about the usage, but also there's temperature, right? The hotter the temperature, the more the electrolyte is working, the faster it will decay. So I may not get 5 years in a very hot environment. The electrolyte might be used up in 2 years, 3 years. Likewise, cold. Cold will extend the life of the battery, but because the electrolyte is frozen and it turns into a gel, I don't get the power capacity out of the battery. Anyone who's tried to start a car in the winter, right? It's actually better for the battery, you just can't get the juice out of the battery. So again, temperature affects the lifespan of a battery. The other piece that does it is charging, right? What I do, remember, I have a depleted battery, I put charge into it to get the electrolyte working until I'm at 100% utilization. But then if I continue to charge the batteries, calling a float, what I'm actually doing is I'm continually trying to put more charge into a 100% charged battery. It's not an efficient process. I'm losing a sliver of capacity in that. And we took that after many years of experience with this, we actually took that into mind and we said, you know what? We can't change the temperature. We can't change the usage. But we can change the way we charge that battery. We can change the way we operate with that battery. So we really developed what's referred to as advanced battery management. And what it says is, hey, when I'm completely depleted, I need to get the maximum amount of power back because I don't know when I'm going to need it again. So after a 15-minute power outage, once power comes back, I may have another 15-minute power outage, so I need to get as much juice back as possible. So I'm going to do a high rate of charge to get to 90%. I'm then going to float the batteries to top it up to 100%. Once I have a full battery, I'm then going to turn off and let the battery sit there fully charged. And I'm going to monitor it, of course. And if I need to, the charge is still there and it has the power. But if I don't need it, I'm going to monitor it. And once I reach another set point, then I'm going to start the process again. Charge it back up, top it up, turn off. Well, Panasonic did a study and found that this technology turning off, versus trickle charging effectively doubled the life of the battery. Under accelerated tests, using ABM doubled the lifespan of the battery. And that's why we're confident on a level 9 that we should be getting that 5 years of the full expected life out of a battery system. So again, ABM doubles the life of the battery, but then it also provides an additional functionality. And that is, by going through this charging process of where I charge the battery at a high rate, I float it over a period of time, and then I turn off and I let it self-decay, I'm monitoring the battery performance, right, over a longer period of time. I know how well it assumed the charge. Over time, as the battery ages, this curve is going to drastically differ. It may not assume that charge. It might take a longer time to do that charge. When it's in rest mode, it may decay faster as my battery depletes. Because of that, I can now compare one graph, one iteration to the next. So if I'm doing this test every 28 days, I can start monitoring as something's going to fail. Everybody here has a cell phone. I'm going to make that assumption, right? And you know, when you buy that cell phone and you first plug it in, you seem to have 2-3 days of usage. Now, loads change, things differ, but you notice that 6 months later, a year later, I charged it in, and no matter what I do, it seems to be dead by 11 o'clock or 1 o'clock. Well, some point in between there, you do come to the realization that, you know what, maybe I need to change my battery. That's what this allows you to do. It tries to predict that failure mode, or tries to predict it in the future. So it establishes the baseline and then compares each battery system against the curve and tries to predict the failure. And in fact, what it will do is it will predict the battery failure about 60 days ahead of it occurring. Right? It's not an exact science. But because we utilize the ABM, we can have that ability to predict failure before it occurs. So when we're talking about availability, when we're talking about mission critical, if I can eliminate failures before they occur, I mean, my MTBFs are non-existent, right? It's a moot calculation if you can eliminate the failures before they occur. So we talked about how to select UPS, how to pick all the pieces, how to work the features into it. We also talked about the different technologies. And we saw that the online double conversion provided a lot more, for lack of a better word, proactive or alarming or sensing or intelligence into what's going on. We also talked about the battery, and we talked about how ABM extends the life of the battery, but also, and critically more important, tries to predict the failure of the weakest link in a battery system or a UPS system. So we went through that. I'd like to now talk about, great, the UPS is doing it, but how do we know? Far too long, UPSs and critical power components have been in the utility room, in the electrical room with little to no communications to them. A gentleman earlier talked about the big power outage we had a few years back, now almost a decade now, back, and he said, hey, what was that like? What happened there? Well, a lot of people realized that their UPSs weren't working. A lot of people realized that they hadn't looked at their batteries in 7-8 years. A lot of people realized that, you know, generators don't necessarily go on forever. A lot of people came to a lot of realizations then. And really, that can almost be seen as the piece where people said, I will not be caught unaware ever again. I want to know what's going on. I want to have the data. I want to have the communications. I want to start being proactive about power. So this really brings us back to communications and tying the pieces in. If we can't collect the data, if we can't assimilate the data, if we can't manage the data, then we can't be proactive and take a proactive approach to this puzzle. So really, when we look at UPS and power quality from a UPS perspective, all a UPS really does, sure, power quality, it eliminates that, but in the event of a power outage, it simply delays the power outage by the length of time I have on battery. So if I have a 10-minute battery, rather than failing at midnight, the UPS decides to take over and give you 10 minutes of grace to fail at 12:10. Power typically would come back in that window, and it would be a non-event. Life would carry on. But what happens when power doesn't come back on? That's where you have to, you're basically given 10-minute grace to perform functions, to perform actions, to take actions. When I'm talking about IT equipment, everyone has a laptop or a desktop computer. How do you shut it down? You go start, shut down, and bring it right down. Why? Because when I come in the morning and I hit the on button, I want it to just gracefully come back up. If I simply was to disconnect power and unplug the battery, it would crash and it would take me a long time to come back up. So in that 10 minutes, if I have an extended power outage, if power hasn't come back on, I want to gracefully shut down the IT equipment. I want to gracefully bring it down so that when power comes back on, it'll come back up gracefully. Also, when we were talking about distribution, I talked a little bit about power management and some of the capabilities, and I really only touched the tip of the capabilities there from what we can do from a control and management of power. But the communications is what collects all that data, brings it into one vision, brings it into one screen, and allows us to now utilize that as the tool to drive the business. So how do we communicate to UPSs out there? Really three fundamental means. Contacts, also referred to as your summary alarms, open collectors from a transistorized relays, form C. There's industrial relays when we're getting into 120 volt rated relays. So numerous different options of basically a yes, no, or a relay indication. Second piece is serial, right? RS-232, RS-485, USB, point-to-point, peer-to-peer, where we're collecting data, getting information out of the UPS. And then the third is a network type of piece. And I'm going to break down these in a little bit more details. When we talk about contact closures, I'm really talking about a flag symbol. From a UPS perspective, really four alarms. They are UPS available, UPS on bypass, UPS on battery, and UPS on low battery, right? You're about to shut down permanently, right? So those are your typical four relays, but they're just yes, no's. So I have 8 pieces of discrete information. Yes, it's of value, but it's limited value at best. Serial communications, typically point-to-point, peer-to-peer. Great when I have one UPS and one system, right? Because that's my system, that's where I'm collecting all the data, it's all there, and we use this serial communications to bring it across. And again, depending upon the capabilities. Typically, a serial port will be housed on the back of the UPS. Also, we get into a Modbus RTU card. A lot of UPSs today, because of the criticality of communications, they have a card slot. And you put in a communications card that is applicable to the environment in which you're communicating. So in this particular case, we would take a Modbus card into the UPS itself and connect the Modbus card serially onto a Modbus network. Right? Piggyback upon the generated PDU onto this network through a gateway onto our Modbus network, and now I'm using a building management system in the building view, and I'm collecting the data, uploading the register maps, mapping it all out, bringing it all in, and now it's part of the overall system. Network communications, once I kind of take that leap across the Modbus RTU, network introduces two people. It also brings an interesting thing to the forefront. And it's probably one of the most appealing parts of the UPS piece in my world is I get to talk to facilities, electrical, the engineers, but I also get the chance to talk to IT managers. And it's a big divide there in terms of the communications, in terms of what they're interested in terms of what they're monitoring. Right? The IT community is monitoring server performance, bandwidth issues, those kind of parameters, really driven around the data processing end of it and the communications end of it. The facilities group is really talking about the power itself. So when I'm talking to IT, we're talking about SNMP communications to third-party managers, Computer Associates, Unicenter, Tivoli, NetView, HP OpenView, and some legacy systems. We're talking about HTTP, web browser connectivity. We get into the SMTP, the email servers, notification of alarms. Even in a lot of cases, Telnet, right? Some remote sites where we'll telnet in there to collect the information. So it's a different kind of world from the facilities, which has traditionally been a Modbus TCP IP talking to a Siemens or Honeywell or a building management type of system. What the UPS does is it kind of bridges that gap between the two. And once I put the UPS onto the network and given an IP address, I can then communicate to the different worlds and interoperate across from. It's an intelligent node on the network, right? It's very similar to how the printers are, where I can put an IP address directly onto the UPS as a node on the network, or I can connect the UPS serially through a server and then put the server as a proxy agent to see onto the network. By far, the most common is to simply go peer-to-peer or point-to-point directly to the UPS. And once the UPS is on a node on the network, then anyone can pick it up. The UPS card becomes my email server. So what will happen is the card will send me an email when it goes into an alarm condition. My email comes, I can very quickly pick up the email and say, oh, okay, it's the UPS at home, or it's the UPS on the 14th floor calling me. So very quickly, I'll go to my web browser, and I'll log into that UPS. Okay, what's going on, right? Overload condition. Well, okay, let me turn off a couple receptacles. Let me turn off a receptacle here. Let me do a little bit of load shedding and get this thing back up, right? Hey, my current draw on this plug went from 10 amps down to 0 amps. Why is that? Well, it's because my router locked up. The device isn't operating anymore. Okay, let me turn off that receptacle, turn it back on. A lot of functionality that we didn't have before, right? And that's the benefit of networking the UPS directly onto the network versus, hey, if this server locks up, I lose my UPS. I'm dependent upon another device, and you want to eliminate single points of failure. What we found out as well is once we started deploying these solutions, the customer base, the marketplace said, well, you know what? Hey, the power is a critical piece of it, but so is cooling and humidity and all these other parameters around it. Can we possibly somehow pick up the temperature from the UPS? So we started monitoring temperature ratings within the UPS as a means of indicating temperature flow within racks, within enterprises. Well, we went one step further. We created this environmental monitoring probe, which will bring in temperature and humidity, as well as 2 additional relays, tie it into the card itself, and then use that card communications to send it out. So to piggyback the communications of the enterprise. So it really provides all of this plug-in, the information onto the network. Now, I can use my web browsing ability, if I can remember all of the IP addresses of all my devices, I can use that and I can do it manually one by one. As I'm loading the devices, I can create screens and views within my third-party tool or my existing managers to communicate to these devices. They're all open source, fully programmable, but you have to load register maps, upload and compile MIBs in order to make it work. Eaton has also provided a software called the Intelligent Power Manager. And the next handful of slides here, which conclude this presentation, really just spend some time going through the slides and see how easy it is to start managing all these multiple devices. Because it's not uncommon to have 20, 30, 100, thousands of these devices across a large enterprise. So the basic screen view is really something we're very familiar with. It's a tree structure. It's auto view, auto import. So I load up the software. I say, go search. Go look for all the devices. So all the IP-enabled Eaton devices are suddenly kind of mushed together, brought in, and put onto the main screen. I then have the ability of taking those devices and just creating folders. You know, new folder, 14th floor, put these 3 devices in there. New folder, 18th floor, put these 5 devices in there. Oh, new folder, building A, put the 18th and the 14th floor in. So that's how, as simple as it is to create my view. I can also then, once I look at the devices, I have the ability to go in and say, okay, you know what? These 4 columns are the important ones, right? We all have Outlook and mail servers where all of our screens are different because I really care about when it was sent. I care about this. Same thing with power quality devices. Give me the relevant information that is applicable to me. On the right-hand side, you have the relevant more detailed information per device. So I just click on a line, and now I can see, okay, that's a UPS. Here's my percent loading. Here's my alarms. Here's my load profile of that device. Now, if I need more, I can double-click, and now I have a window directly into the device. So I'm talking to the 14th floor directly. I don't need the management software chewing up bandwidth, creating more issues from a networking perspective. I just need a summary, and if I need to go get more information, if I need to collect it, I'm going to go directly to the point and find it. And here's just a screen from picking the menu screens I want. Here's an indication. This particular PDU with, what's that, 4 times 4, 16 outlets, they're all green. Right? They're all green right now, indicating they're all powered on. At any point in time remotely, with proper security, proper passwords, proper access, I can go and turn off those receptacles. Either power up or power down. Again, the opportunities of management are endless. Another big struggle with enterprise type of deployment of power quality in UPSs is the upgrading. Nobody builds an enterprise at the same time overnight. It's always staged, always deployed over a period of time. The biggest challenges, particularly with software, is upgrading and ensuring commonality, ensuring latest level of compliance, particularly with security, right? Security enhancements. It's not about features, it's not about capabilities, it's more about security enhancements on networking devices. So you need to have the ability of doing a mass upgrade and the ability. So the software allows itself to automatically go out to the devices, upgrade them as need be, make sure everything's current and make sure everything's filling in and really delivering to the same level requirements. Another big critical piece is asset management. As we start deploying hundreds of devices, which is the better way to do it, quite frankly, helps and benefits, again, we talked a little bit about this yesterday, but it really helps a lot of those capabilities, is a deployment. But the challenge is, how do I manage 100 devices out there? How do I know what's everywhere? And what the software allows you really to get into heavily is asset management, where I can define the user screens, I can get the serial numbers of the individual power devices, but really, my goal in life, I wish people woke up in the morning and said, I need to get more UPSs, or I want to get more UPSs just because I love UPSs. That doesn't happen. The reality of it is there's critical loads we need to protect, and the UPS provides me clean, filtered, regulated power. If it wasn't for the loads, people wouldn't buy UPSs. It's a harsh reality of life. So the software does one step further. Not only will it track the serial numbers for UPSs, which is nice to have if you're a UPS person. But most importantly, and more importantly, is when I click on that serial number of UPS, what loads, what's the functionality, what is that UPS protecting, right? That's what we really care about, right? When the email server goes down, you really want to know what application is running the email server, not which UPS. So again, incorporating power management, incorporating this ability, the proactive alarming, all into one. And at the end of the day, it's about driving the loads. It's ensuring the integrity of the critical operations. It's ensuring the integrity of the downstream. And that's really what we're talking about delivering here. Over and above the UPS, we talked about picking the right UPS, some of the challenges, but it really comes down to this about bringing it in as a useful feature and a useful functionality within the enterprise. So, as I'd indicated, the top questions really help fiddle through the minefield. And then around item 6, we start switching into more proactive of saying, okay, great, I needed to buy that system. I needed to put that solution in place. Now let's make it work. Let's make it work for the expense. Let's use it as a tool to drive the business as opposed to be at the mercy of it.